Lesson 1 has us covering some basics of shared storage. We're going to look at some different technologies that vSphere has for accessing external as well as hyperconverged vSAN storage. So we're going to have a look at both how we access that and then what types of data stores we create based on those types of architectures. So what's a data store, right? We've used this word data store a bunch of times. Think of a data store as a formatted file system or formatted storage location for your virtual machine files, right? Now, a data store, like any other sort of file system, can store lots of different types of files. You could put an Excel file or a PowerPoint file on a data store. I'm not sure why you would, right? Because data stores are built with virtual machine files in mind. That is, the large VMDK virtual disks and the small VMX files. Those sorts of things all reside together in data stores that can then be accessed by multiple hosts at the same time. We're also going to have things like ISO images there because those are a data store is a nice place for a centralized location for ISO images, as well as templates that we can then use to deploy other virtual machines. Now, vSphere supports VMFS data stores for block level storage, NFS data stores for file level storage, vSAN for hyper-converged storage, and something that we call virtual volumes, which takes the concept of vSANs where we have object-based storage and moves it to an external storage array so that ESXi and vSphere in general has a little bit more control over the utilization of the storage and the different areas of storage, whether it's for example, SSD versus spinning disks, and whether or not you want encryption or compression or deduplication. All of those rules for your virtual machine files can actually be created not at the storage array level, but actually at the vSphere level. So it gives vSphere administrators much more control over the environment. And that's true for vSAN with internal storage and virtual volumes for external storage. So a data store is simply a location for virtual machine files that can be accessed by multiple ESXi hosts simultaneously. So let's have a look at this diagram where we're going to look at the different types of data stores, and we're going to see the protocols or the transport mechanisms that are used to access these type of data stores. Now, don't forget here that at the top, we have our ESXi hosts where our virtual machines are running. And those virtual machines come in the form of a set of files, obviously. So those files then are placed in data stores, and we have 4 different types of data stores, be it VMFS for block level storage, okay? And when you have block level storage, there's a couple of different transport mechanisms that you can use. You can certainly use what we call direct attached storage. So these are storage devices like SSDs or spinning disks that are internal to your ESXi host that are connected to some sort of controller, storage controller, SATA, SAS, those sorts of NVMe, that sort of thing. But those are accessed only by a single ESXi host. So when we talk about direct attached storage, we're not talking about shared storage. It's just storage devices that are accessible only by the ESXi host that is internal to. That is opposed to vSAN storage over on the right-hand side, where it's also direct attached, but we use a network on the back end to connect multiple hosts to each other, okay? So when we're looking at VMFS data stores, if it's direct attached, it's local, a local disk. Now, when we have fiber channel, okay, for VMFS, we're going to access it over a fiber channel network, so a SAN, for example. We also have what we call fiber channel over Ethernet, which combines special hardware to access both fiber channel and our Ethernet networks over the same set of infrastructure, the same switches and the same cables. And finally, we have iSCSI. And iSCSI is a way for us to access SCSI LUNs using TCP/IP transports. All great stuff, right? And all of this is done at block level storage, so we create a VMFS data store. Now, when we create an NFS data store, it is a TCP/IP Ethernet transport, okay? And we're connecting to a storage array that provides us a file share, similar to a Windows file share, but not Windows, right? Or actually, you can do NFS on Windows, but not the Microsoft CIFS file shares, but this is the Unix or Linux-based NFS file shares. Okay. Sometimes we call these NAS arrays, and there are lots of different vendors for really powerful, highly capable NFS NAS arrays as well. Now, when it comes to vSAN over here, we're looking at internal storage that are shared by multiple ESXi hosts that then access each other through an Ethernet network. And then finally, we have virtual volumes, which can use Fibre Channel, iSCSI, or NFS type transports to access what we call a storage container. Not a LUN, but a storage container. This is a new concept that we have, but essentially it allows ESXi to treat each of those virtual disks as its own volume. And we can then apply rules to those volumes to make sure that each of those virtual disks or virtual machine files can give us the performance and the capabilities and the capacity that we as vSphere administrators require from them. This is another chart that dives a little bit deeper in terms in defining the features that are supported across each of our data store types. So when it comes to VMFS, we can do Fibre Channel over Ethernet, iSCSI. New in vSphere 7 is iSCSI, is iSARE, which is iSCSI over remote DMA, okay, as well as NVMe directly over remote DMA access. We also have direct attached storage, which can be done with SAS controllers, SATA controllers, or NVMe. Now, when it comes to VMFS, if it's external and there's a LUN that we can boot to, we can actually boot ESXi from it. We cannot boot for iSCSI over remote DMA or NVMe over fiber either, or over fabrics either, okay? Now, since direct attached storage isn't considered a SAN, it's not a network, it's just a local attached storage, it doesn't really apply to boot from SAN, but you can certainly boot from direct attached storage. Now, vMotion support. What do we mean by vMotion support? Well, in order to have vMotion, we have to have the same storage accessed by multiple ESXi hosts. So in other words, shared storage. So do we support vMotion? Yes, for this. Now there's a little asterisk here over by direct attached storage. If we have an ESXi host on one hand and an ESXi host over here, and they both have direct attached storage, if you want to do vMotion, what we have to do is not only move the virtual machine from one location to another, but we also have to move the virtual machine files over one another. So that takes vMotion and combines it with something called storage vMotion. And in that case, we sort of pseudo support direct attached storage for vMotion, but there's more involved there and certainly more work that we have to do to move the virtual machine files. It's certainly a little bit less efficient than having shared storage. Now, in order to support vSphere HA, which says that if an ESXi host should fail, I have another ESXi host that can run those virtual machines, we do have to have shared storage. Okay, so all of these apply except direct attached storage. And finally, DRS, our distributed resource scheduler, which balances the load across multiple ESXi hosts by moving virtual machines back and forth. Okay, DRS is supported for shared storage. Now, when it comes to NFS, we're using an NFS storage protocol. The boot from SAN is not supported on NFS, but all of these other features are. For virtual volumes, also boot from SAN is not supported, okay? But vMotion, HA, and DRS certainly are supported. And the same thing goes true with a vSAN data store. It is shared storage, but we don't support direct boot from it. In the case where we don't support direct boot from shared storage, in this case, all you'll need to do is provide another boot device on your ESXi hosts, whether that be a USB device, an SD card, an internal hard disk, or SSD, those sorts of things that we typically understand are boot devices in computers. So VMFS. VMFS was developed by VMware as a highly performant system for managing virtual machines, their very small files in their metadata files, and their very large virtual disks that can be accessed simultaneously from multiple ESXi hosts. So VMFS has gone through several different revisions, each revision adding performance and capabilities and features to the VMFS data store. The current version of VMFS is VMFS 6, okay, which provides concurrent access to shared storage, dynamic expansion, meaning that we can grow a VMFS data store if we have access to extra LUNs, or we can increase the size of a LUN, without having to shut down that data store and move the virtual machines off of it. We also provide local on-disk locking. That is, if an ESXi host has access to the shared storage where a virtual machine set of virtual machine files live, and that host wants to power on a virtual machine, the host can tell the VMFS data store, please lock those files and make it exclusive to me, so that another ESXi host can't go and try to run those virtual machines at the same time. Okay? If one virtual machine decides to give up that lock, that's fine. We can do vMotion, or we can do HA and those sorts of things. VMFS 6 added support for 4K native storage devices, as well as automated space reclamation when it comes to thin provision disks. When we delete files or we delete data from a thin provision disk, the VMFS 6 data store will automatically reclaim that space and hand it back to the storage array. Now, here we're looking at NFS, and I want you to have a look at the difference between the two pictures. So here's NFS, and here's VMFS, the previous slide. It's the same picture, right? You have hosts running virtual machines that have access to a data store. Here we have hosts running virtual machines that now have access to the same data store, except now it's not a block level storage array where we're accessing LUNs, it's a file level storage array where we're accessing file shares. In vSphere, we currently support NFS version 3 as well as NFS version 4.1 over TCP/IP. And in the later lessons, we'll look at actually how we connect to these. Next, we have vSAN. Now, like I said before, in our hyper-converged infrastructure, what we're trying to do here is use internal devices and share those internal devices across multiple ESXi hosts using a network on the back end. Now, with vSAN, all of these capabilities are native to vSphere. So all of the mechanisms happen within ESXi, and it's all managed by vCenter Server. So here's the idea. In each of our ESXi hosts, anywhere between 3 and 64 ESXi hosts in a cluster, we're going to place storage devices. Okay? We're going to have at least one caching device, and that caching device has to be solid state. And then we're going to have at least one capacity device. And our capacity devices across our vSAN data store, or across our vSAN cluster, can either be spinning disks, or if you really want to perform well, really well, we'll have solid-state devices or NVMe devices. Okay, so you're going to place at least one caching device and at least one capacity device in each of these ESXi hosts. We'll connect them with VM kernel ports over a network, and that will create one very large aggregated vSAN data store for us. Now, when it comes to virtual volumes here, we're taking our external storage arrays connected via iSCSI or Fibre Channel or NFS, one of those protocols, and we are accessing them as shared storage like we did before. Except rather than having block level storage, we're going to have something called object-based storage, where ESXi has an idea itself as to the capabilities of the storage array and treats every single file in this object-based storage array as if it were its own volume. Now, your storage arrays themselves have to be virtual volumes aware and have to support virtual volumes because the storage arrays are also aware of these objects. Where in traditional storage, the storage array only knows about the LUN. It doesn't know about the requirements of the files on the LUN. It doesn't know about the virtual machines that are running on the LUN. It just says, I have this LUN. It's made up of spinning disks or solid-state disks, and it's this amount of capacity. That's the only thing the array knows. But in virtual volumes, the array knows that's a virtual machine. That's a virtual disk. And ESXi and vCenter have asked me to encrypt that virtual disk and place it on solid-state storage because it needs a certain amount of IOPS capability, and it needs a certain amount of capacity capabilities as well. So what we're able to do with this object-based storage is actually make really, really good use of our storage capabilities on our storage arrays, but we're able to do it and manage it all from the vSphere side. So that gives us a lot of capabilities. We do this through a set of APIs called the API for Storage Awareness. Virtual machines can also access LUNs directly through something that we call a raw device map. This redirects the I/O from a virtual disk straight to the LUN that the ESXi host has access to. Now, there are a few reasons we might want to do this, but as the capabilities of VMFS over the years have increased, those reasons have diminished. We might do this, for example, for LUNs that provide a quorum for clustering capabilities. For example, for Microsoft's failover cluster services where we're using a quorum disk as opposed to a quorum file, or Oracle RAC, which provides a database quorum system where multiple databases need to have access to a LUN together to provide that quorum for clustering capabilities. Okay? So the idea here is what we're going to do is we're going to redirect the output of a virtual machine's virtual disk from a VMDK file to a raw device VMDK file, and then over to the actual LUN itself. Okay? There are a number of considerations that we need to keep in mind when it comes to physical storage. Okay? All of this will go into the decisions that you make around what type of storage do I implement, what type of storage capabilities do I need from my particular virtual machines, and so on. Think about the sizes of your LUNs. Think about the bandwidth required for your applications. Think about the requirements of your applications for IOPS versus the capabilities of the LUNs for IOPS. If the LUNs are created with spinning disks, they'll have far fewer IOPS capabilities than those LUNs that are created from solid-state devices, for example. Think about things like disk caching. Think about things when you're considering fiber channel, like zoning and masking, making sure that each of your ESXi hosts can see each of those LUNs with an identical presentation. Think about multipathing. That is, how do I avoid single points of failure when it comes to accessing my storage from an ESXi host? Think about NFS and how and with what sort of authentication mechanism my ESXi hosts will access an NFS file share. All of these things we're going to continue to talk about as we dive into each of the different particular types of shared storage, right? So that gives us a pretty good picture of our vSphere storage technologies and the different types of data stores that we create. And as we move forward, we're going to have a look at how we actually configure these types of data stores from the perspective of ESXi. So we'll be pushing buttons and twisting knobs and doing lots of labs. We'll talk to you in a few minutes where we'll look at fiber channel storage.